Oh, hello. Welcome back to the continuing lecture in investments. So let's take a look at our um, uh, uh, let's take a look at this example once again. I mean, this is not the same thing because uh, if you remember um, in our last session, right? Um, I was, um, I told you it was a bit, and in previous session, right, before the last one, um, the optimal, investment, the investment opportunity frontier was a little undulated or a little off, and the reason was because um, the data were uh, off. I mean, the data for that example, because we're trying to find the minimum variance portfolio, uh, or the weight for minimum variance portfolio, right? And that by plugging in all these different uh, the combination of weights, uh, it would automatically generate, right? This, opportunity, investment opportunity sets, and automatically, uh, connecting those dots would automatically generate the frontier, right? In the investment opportunity set frontier, right? And as we were doing that, right? I discovered, the data for expected returns and, standard deviations were not the ones that we uh, calculated from the previous example. So I corrected those data values, and I was wondering, where did that come from? Where did that actually it came from? It came from the new example. Another, and you might wonder, isn't that the same example? No, this is not the same example. This is the example for actually, this is the exercise for uh, maximum Sharpe ratio, maximum Sharpe ratio. So this is not. I shouldn't call it maximum Sharpe ratio. I mean, it's variance, of course. Maximum. This is the combination of the investment opportunity uh, set that would maximize the slope of this capital allocation line, which is called, Sharpe ratio. Of course, the Sharpe ratio, the, the Sharpe ratio is uh, because it is a slope, it's the line that is tangent to the investment opportunity frontier, right? And then it's not, and then it's not this point that we want to find. In other words, it's not the minimum variance, but we want to find, uh, obviously, the Sharpe ratio at this point. The Sharpe ratio at, this is Sharpe ratio of the optimal portfolio, right? Optimal risky portfolio. And then the Sharpe ratio of, which is, this is the maximum Sharpe ratio. Of course, Sharpe ratio at that point is greater than, this Sharpe ratio is clearly higher than or greater than this Sharpe ratio at this point. In other words, the line tangent on this curve, the slope line that is tangent to this curve at this point is clearly higher slope, right? Greater slope than the slope line that passes through this point, right? But for that example, somehow they gave different um, different data set. I also calculated this in the previous example with these data values. I also found the optimal the weights of stocks and bonds for a maximum Sharpe ratio point. So in other words, that's the Sharpe ratio, the weight that maximizes the Sharpe ratio of the optimal risky portfolio, right? I calculated that based on this, but this was not. It was just mechanically done. But this was not. Let me take a look at that. And this is the number that is, basically given by. But this one was just done mechanically, and I'm telling you, there was something missing here because, first of all, if you look into the formula, right? I need the risk premium, and to take the risk premium, and this is not right. This is, this is not this formula, right? And basically, this has nothing to do with this formula. So it was just, it just tagged along because this doesn't need to be here, actually. It just tagged along. Okay. So actually, this doesn't need to be here. It has nothing to do with this minimum variance, example. But now, so to calculate, Sharpe ratio maximizing weight, we need, the formula requires, risk-free return. And the previous example, there was no risk-free return, right? So we need basically, new data set. So in this example, expected return is, this is given. This is not from any of our past examples. Expected return on the stock portfolio and expected return on the bond portfolio. And risk-free return is given, right? Which is 5.5%, which is, exactly, this point. It starts here, right? That's risk-free, right? Risk-free return. And then, let's do this example. I already did it, but, just to, first of all, we need, we don't need to redo this, but, just to simply, fill this, the data set, right? To fill this data range, we'll find still minimum variance, right? Weight. I'm not gonna redo that. I will leave it like that, and this I will basically, show you how it is done, and the rest of it, just right. Okay, and this I will do that again. And the name should be maximum Sharpe ratio. It's not far, but maximum Sharpe ratio. So maximum Sharpe ratio point, or the investment opportunity set that maximizes the Sharpe ratio. But because this column is still, variance, I guess, it's not that wrong to call this, maximum Sharpe ratio variance. If it is, pointing to this variance, right? Okay. So basically, this is the formula for the bond, right? The weight for the bond for that, maximum Sharpe ratio point. And then this one will be 1 minus that. 1 minus L2. And so calculating this, I just follow the this formula. Risk premium of the bond times, and then as I told you, it's basically the structure is based on this specification, right? This formula specification, and it's just weighted by the risk premium. For the variance of the stock portfolio, the risk premium is multiplied is the bond risk premium, and so it's all, like switched, right? For and take a look at this, for this is what covariance, right? Covariance of, for covariance then is, a stock risk premium, right? And then for bond variance, the multiplier is the stock excess return. And then because this is 2 times covariance, so we have, both uh, stock risk premium and bond risk premium, right? So that's what is being done, right? The bond risk premium, right? Times, D2 squared, which is stock variance, and then B2 minus C2. It's actually B2 minus that. Oh, that has to be, so that is not B2 minus C2, but A2 minus, I think. That was, made a mistake there. A2 minus. Okay. And then divided by B2 minus C2 times stock variance, and then A2 minus C2 stock risk premium, and then E2 squared. E2 is the bond variance, right? Plus A minus C2 stock premium, stocks, risk premium, bond risk premium times covariance. G2 is covariance. It's really, nice. It makes it easy when you have covariance, right? Already as a product of, standard deviation of A, standard deviation of Y, X and Y, and correlation, right? Product of that. So if you do that, I got this, right? And then all we need to do is simply, then find the expected return, because, the vertical axis, we will have to have expected return. And then on horizontal axis, is our standard deviation. So it's basically weight times, okay, expected return on the stock, and you lock it, plus weight times B2 and lock it, right? And then there you go. Okay. And then variance. We know the variance of the portfolio is, first of all, weight times, I'll have to square them all together. So weight times standard deviation stock squared plus, I'll have to lock this first, D2. Hit F4 and lock it. And then weight times then and then plus 2 times the covariance, right? 2 times, not just that, the weight, I'm sorry, I forgot the weight, 2 times the weight of, right? And then the weight of bond times the covariance. Covariance, I'll have to also, oops, what happened? I have to and then back. Okay, and then the standard deviation is the QRT, square root of variance. And now all you need to do is just drag it down, and all right. And as soon as I've done it, automatically, it will plot, right? And then, because I already, I already gave the command, I already, this, graphing, I have, already embedded the graph to reflect the data set. So finally, I just simply, take care of, some housekeeping thing. Okay, and last but not least, the bottom borderline. So the whole table will look, very hunky-dory. Now, so as we look at this, then, we understand why, everything that has been already, explained is confirmed, right? Our at this point, where the and look at the value of our maximum Sharpe ratio point. Standard deviation is the return is about 12.88. This is about 12.88. Standard deviation 23. This is about 23 because this is 25, right? There you go. So this is our example of how we find the Sharpe ratio maximizing weight. Okay, and then let me switch to stop sharing this and switch back to our so here we go. So then, how do we construct our risky portfolio with, uh, three assets or three stocks? I mean, we have basically, risky portfolio consists of, two portfolios, stock and bonds. And within the stock portfolio, uh, if we have a stock portfolio will, consist of uh, almost at least like 20 stocks to make it, well diversified, right? So how does that work? Yeah, so we all know that as this frontier moves, to the northwest, right? To the northwest, it is more, it's a preferred combination, preferred, uh, investment opportunity set, and um, by including more stocks into the portfolio, right? Uh, it will inevitably, eventually, move the frontier to the northwest. Uh, so it works, logically, step by step. It works this way: curve passing through A and B, and A and B are 2 points on uh, constructed by these two assets, right? Uh, and curve passing through B and C, right? That's also a portfolio, right? Consisting of these two stocks. I mean, um, within the stock portfolio, these individual stocks, when you have two of them, it's a two or more of them. It's also a minor, smaller, portfolios, right? Yeah. And point E on AB, right? And point F on BC curve are, and these 2 points, E and F, are two portfolios. Uh, these are two, actually, stocks, right? Chosen from the set of AB and BC combinations. I mean, if E is on this frontier of A and B, right? Uh, it's E is like the part of the AB portfolio, right? So it's a portfolio consisting of three stocks, and then F is on the frontier of B and C. So then it is a part of, it's one of the assets, BFC portfolio, right? And then and if you construct a portfolio of two stocks, E and F, this portfolio is basically uh, uh, more north and more towards the west, right? Now, suppose you are repeating this over and over, right? So many with like 20 or 30 stocks, you're repeating this over and over. Curve passing through E and F is a portfolio constructed from portfolio E and F. Since E and F are constructed from A, B, and C, this curve shows some of the portfolios constructed from three stocks. The curve EF extends investment opportunity, right? Investment opportunity set to the northwest, which is the desired direction. So eventually, this way, the investment opportunity set frontier move more and more, can be moved much further to the northwest, right? So you continue to take other points from these three curves and further combine them into new portfolios, then shifting the opportunity set even further to the northwest. This process would work even better with more stocks. Yeah. 20, 30 stocks. I mean, 20 stocks already reduces um, uh, the non-systemic risk to almost to zero, right? Moreover, the boundary or envelope of all the curves thus developed will lie quite away from the individual, right, stocks in the northwesterly direction. And this envelope, right, this the boundary frontier is called efficient frontier of risky assets. Efficient, because they nothing can do better, right? Nothing can give you higher returns for the given standard deviations, right? So that's the most efficient, right? And so we already, we're starting to talk about. So I'm not going to go over this again. Efficient, meaning, it gives you the maximum Sharpe ratio for the complete portfolio. And complete portfolio consists of optimal risky portfolio and risk-free assets. Optimal portfolio capital allocation line is tangent to the efficient frontier. We already know that. Portfolio manager offers the same portfolio to all clients. Basically, yeah, think about it. If you're an investor using a fund, right, mutual fund or equity fund, basically you are exposed to the portfolio manager's efficient frontier, right? So it's the optimal risky portfolio, all possible combinations on the fund manager's uh, investment opportunity sets, and individual differences are simply where you are. I mean, if I'm not a very if I'm a not a very risk tolerant investor, if I'm extremely risk averse, right, I'm going to my combination of I will be somewhere here. I will be somewhere. I will be somewhere. If I'm a more risk taker, I mean, as long as I'm on, let's say, I don't want to. Okay, let me draw this again, or I'll have to stop draw. Insert. Or that's too slightly like this. Okay. I want to make this. Okay. So, I will be on. well, I may be, if I'm very, risk averse, I may be here. If I'm more risk tolerant and if I'm a risk taker, I may be there, right? So in other words, the portfolio manager can handle, right? All clients, with different risk tolerance, right? So more clients select their own, their desired point of, on CAL. More risk-averse clients will invest more in risk-free assets and less in the portfolio. And then the less risk-averse clients, both will use portfolio optimal risky portfolio, or as their optimal risky investment vehicle. So this gives rise to the preferred portfolio. This gives rise to separation property. Separation property means, it was developed by, James Tobin, 1958, and the name Tobin once came up, at the beginning of this semester, right? Was Nobel laureate in 1983, and you remember Tobin's Q? Yeah. Separation property implies portfolio choice into two tasks. Optimal risky portfolio is a purely technical problem by analysts, and portfolio complete portfolio is a personal choice of best mix of risky portfolio and risk-free assets. Okay. Now, this took a lot of time already. I guess I will have to stop the video at this point and continue in the next video. Stop recording.